Hi, I'm Cesar Wiratama, lead engineer from P2 Tensor with experience in simulation since 2013. We will explore running a flow in a globe valve in this tutorial. We will calculate the velocity and pressure distribution and then predict the potential cavitation. Let's review our workflow. We will start with geometry preparation in Blender, then use block mesh and snappy hex mesh, and finally run cavitating foam in parallel. We will also show how to clean the result after the simulation. We will use Blender to separate surfaces like inlet, outlet, and body for the geometry preparation, then create the block mesh by checking the geometry bounding box, and discuss how to input block mesh coordinates based on the geometry, then discuss the snappy hex mesh setups and their location in the mesh. Also, we will check and edit the boundary conditions based on your specific case before running, and then finally we can run our simulation in parallel using cavitating foam. We will post-process it to calculate the pressure, cavitation, velocity distribution, plot the curve, and make the stream tracer. Then we will also show how to clean these results if you want to change the setups and get new results. Then we will discuss how to use the script files to make your workflow faster. In this tutorial, we will discuss step by step without using the script file first, to help you understand what's happening during each step. Okay, let's begin. First, you can download the template from the link in the description below. To generate the snappy hex mesh, we need the block mesh and the STL geometry. Let's prepare our STL geometry on Blender. First, open your Blender software. Then, open the valve fluid geometry and make sure your scale and unit are consistent. Enter the edit mode to start editing the geometry. Select the surface selection to make our selection easier. Block the surface we want to define, like our inlet, let's say. If you select an unwanted surface, hold Ctrl and click it to deselect. Once you're done, hit P button and click Selected Surfaces to separate the selected surfaces. Do the same thing for the outlet. You don't have to do it for the body, as it will be automatically separated. Once done, export it by clicking the surface you want to export, then click File, Export, and ensure Selected Only is checked. Export these faces to your constant 3-surface folder. Delete the MTL files. They are unnecessary for OpenFOAM simulation. Now let's define our block mesh, the foundation of our snappy hex mesh. First, let's check our geometry bounding box to find the extreme coordinates for our block mesh. Open and edit our block mesh based on our extreme coordinates. For simple block mesh, extreme coordinates are vertex 0 and vertex 6. Input slightly different bounding box coordinates to ensure our STL geometries are inside it. You can change the rest of block mesh coordinates. If you need help editing it, check the basic block mesh tutorial in the description below. Set your resolution here. Higher resolution means higher accuracy and fidelity, but longer simulation time. Once our block mesh ready, now we are ready to edit our snappy hex mesh. Ensure the names are match the name and extensions in our 3surface folder generated from our Blender early on. Let's define our location in mesh. You can check the bounding box of our inlet as a reference, then slightly change in the Z direction to ensure it's inside our geometry. Finally, we can execute the command snappy hex mesh override to generate our snappy hex mesh. The command automatically copies, pastes, and deletes the time folders for the generated cut cells and snapped mesh. Before running our simulation, we must check and set up our boundary and initial conditions. Check the boundaries names to ensure they match our snappy hex mesh names. They are body, inlet, and outlet. Change the mass flow rate inside the U file to check your operating condition. You can also edit the outlet pressure to represent the valve outlet pressure, which might be determined by the overall system flow. The initial condition value can be arbitrary. We can calculate the pressure drop of this system since the inlet pressure is zero gradient. Please check the thermodynamics properties file in the constant folder. This file contains value for your fluid at specific temperatures and pressures of your operating condition. Let's run our simulation using the Cavitating Foam solver. We will run it in parallel with MPI run using 8 processors. If your hardware has a different processor, check the system decompose part dictionary to set the number of decomposition and the processors. Let's run it. It may take a few minutes, hours, or even days depending on your mesh resolution, time step, and end time, which you can set on your system control dictionary file. Remember that cavitation is a multi-phase flow, so keep your time steps small to satisfy the low current number. Once your simulation is complete, run touch valve.foam or whatever name you like to generate the foam file. We can open it on ParaView. Let's check our pressure distribution. We can change the color and the time range for analysis. Then import our solid model to make our model more representative. Using volume fraction of vapor, we can check the region where the cavitation happens. To display the velocity, we need to make the slice view so we can see the region we want in detail. The other important data is the velocity profile. We can plot it over line by creating plot over line filter on our valve foam. We can also see the data in the spreadsheet format. Finally, let's create the streamline by using stream tracer filter. For the final touch, you can change the legend color. If you want to clear your result to rerun your simulation with new boundary conditions, let's say, we have to delete our processors folder and time folders generated. Execute rm-r processor star to remove all the processor folders. Then execute foam list time rm to remove the time folders except the time 0. You have successfully run your simulation and can now change the geometry and other conditions. In this part, I want to introduce you to a way to speed up your workflow. In the downloaded template, you will find scripts like all run, build mesh, clean results, and run. To make them executable, run chmod +x, then your script. And you can do it for all of your scripts. You can simply execute ./blockmesh to run blockmesh and snappyhexmesh override automatically. Then you can execute ./run to sequentially decompose power, cavitation foam with 8 cores, and reconstruct power. Adjust the number of cores based on your hardware. Or you can instead execute all run to execute build mesh, then run sequentially. If you want to clear the times and processor folders, you can simply execute clean results.